Hi, welcome back. Many a times while working with LLMs, we come across this full precision versus quants. Just by the name of it, a full precision might mean that it is highly precise, whereas quants may not be. But then why is it so? Why do we say quants might fail in certain use cases? And then why do we say many a times quants might still be okay? And why do we say quants are higher performing? So I thought I will build an intuition, a mental model around it, so that when you look at a FP versus a quant model, you kind of know what you're getting into. Models, many of the LLM models are autoregressive in nature. So that means that it needs to take the current token or all the past variables that comes with it, the baggage that comes with it, and then it has to predict the next token. While predicting the next token, there are many different weights it has to deal with. And these weights can be highly precise weights. And when we start doing it, between two weights, there can be many tokens that come across. So, the moment we start reducing the precision, there might be a confusion between two distinct models. Whereas a highly precise model can differentiate between two tokens, a slightly lower precise model will start to overlap the meanings of these tokens. Of course, LLMs don't understand English the way we understand English. Greater precision, greater possibilities. So why should I not always pick the highest precise model? That comes with its downfalls too. Increased size, slow in response, higher spec of hardware, you will need better hardwares. So how do we get around this? Because a lot of my use cases don't really require such a big hardware. The answer is quants. Before we understand quants, let us slightly digress a bit, look at a use case and then kind of try to understand what quants mean. Now check this out. I have marks scored against a total marks for say 10 students, and then with a scorecard like this, I am supposed to answer these questions. Declare ranks, rank them on rank 1 to rank 10. And then my company hires people who have scored B and above, B grade and above. So what is B grade? Some kind of a gate. Or question 3 is you need to pass this exam to qualify further. Now if you look at it, all of these questions can be answered with the scores that we have, but then what route do we take to answer them? And there might lie some leads into full precision and quants. Now, because all of these are different total marks, if you have to rank them, a good idea is to maybe derive a percentage for each of this so that these percentages can be highly precise. So, except students who get an exact mark, I will be able to differentiate students to whatever precision I want. So percentage might be a good option for me, and maybe I will use this to declare ranks. Can I use this to say my company hires people who have scored B and above? That's the 60% gate. Yes, I can use this and answer that. Can I do you need to pass this exam to qualify further greater than 50%? Yes, I can do that with this. But then would that be wise? Do I have any other ways of doing it? Why do I call it might not be wise? Because why do I need such a highly precise answer just for me to execute a single gate? So maybe there are better ways of storing the marks. Maybe there are better ways of categorizing these students so that I don't have to always use a highly precise percentage to arrive at my answers. You might have already thought of those. You might have already thought of the answers. Now, let me declare grades. So with these grades, what I do, I create 4 different grades so that I can understand who is A grade, B grade, C and D grades. So this allows me a slight better degree of categorization. While percentages guaranteed me some kind of a 1 by 1 kind of categorization. Now grades allowing me to categorize them slightly more coarsely. Or why not even have another categorization, which is just a pass or a fail kind of a response? Yeah. Now, you can consider this as a difference between a full precision model and quants. While full precision models use floating point numbers to arrive at some kind of a precision, quants will categorize them into different discrete bins. Like how the first quant is separating them into 4 different bins, and the second quant is separating them into 2 different bins. So because it's 4 different bins, it's like a 2-bit quant. And then because this is just pass and fail, the second one, it is a 1-bit quant is enough for us to segregate the students. Now let me see. I want to declare ranks. I want a full precision model because I need to know how to sort them. But if I have to say my company hires people who have scored B and above, this second quant, a 2-bit quant, is enough for me to answer it accurately. If I need to say you need to pass this exam to qualify further, just a 1-bit quant is enough. The gates are much simpler. Now, okay, with different kinds of things I can answer, but then what happens if I use the quant itself to answer all the questions? Now, if I say, hey, I will use this 2-bit quant, but I'll still try to answer the question of declaring ranks, then what happens? You see that student 1, student 4, and student 8 are all bunched into a single discrete bin called as A. So now how do you rank between this? You have lost the precision. You don't know how to rank student 1 and student 4 and student 8 if you use a quant bin. But it will still do a better job. It will still put A first, B next, C next, and D next. But then within A there is confusion, within B there is confusion. Now you get the idea of quant. Now what would happen if I were to use a 1-bit quant? Can I still do a ranking? I can do, but the confusion is a lot more. Between the quants you might still have the right answer, but then within it there is confusion. But then if you look at the full precision, now you have to store a lot of points, you have to calculate a lot of points, and then go through it one by one to decide on all the answers. But with quants, many of those answers are already packed in. So that is what happens when you say that I'm working between a full precision model and a quant based model. A full precision model uses floating point representation, while as quants are all, instead of using a floating point representation, they use discrete bins. FP6, FP16, FP32 are all that many floating point to identify precision, almost giving you the imagination of an analogous representation of numbers. Quants, you can have a 2-bit quant or a Q4 which is 4 bits or Q8 which is 8 bits. What you observe here is the moment you keep increasing the number of quants, you are very, very close to a full precision model itself. So if you are thinking to use a quant which is fast, which is smaller in size, then the quant bit has to be that much lesser. A full precision is more accurate, versus quants are, because there are lesser the bins, the accuracy is lesser also. Full precision, larger in size, they require higher specs to run. Quants, they're smaller in size and they require relatively lower spec to work. So if your use case is just about building some sentences, rephrasing, paraphrasing something, then a quant variant is enough for you. But if your use case requires a lot more thinking to do, a lot more step-by-step evaluation, a lot more flowery and an accurate text, then you are better off using full precision. So that is how you build an intuition between a full precision model versus quants model. Thank you. Signing off with this.